Buenos días, yo soy Inés, hago el doctorado en el Instituto de Energía Solar y, bueno, prácticamente lo que iba a decir yo lo ha contado un poco Jimena. Deciros que estas charlas, nacen un poco de las que se hacían inicialmente en el ISON, desde la TIC también participaba y un poco de ahí nos juntamos un grupo de más de 10 alumnos de doctorado con la idea de hacer algo un poquito más amplio, abierto a más gente y divulgativo. O sea, el objetivo de estas charlas es que sean divulgativas y que independientemente de que hagas tú el doctorado, pues aprendas algo. Entonces, eso, bueno, y que estamos en una escuela muy multidisciplinar y eso es muy positivo, pero también crea barreras de conocimiento entre distintos grupos y centros de investigación. Así que nada, esperamos que den fruto, pues, conexiones y colaboraciones dentro de la escuela y que también para las personas que vienen y que participan pues sea algo que enriquezca profesionalmente y personalmente. Y nada, queremos crear un espacio relajado y amigable y por eso os invitamos a participar, o sea, que deis vuestras charlas, porque ahora estamos arrancando y tampoco tenemos mucha gente voluntaria, un poco por el desconocimiento, supongo. Así que nada, os animamos a participar.
Y nada, bueno, por daros algunos detalles de estas charlas, primero va a ser cada 2 viernes, o sea, cada 2 semanas. Vamos a empezar 15 minutos antes con un desayuno, que también, bueno, yo creo que es un incentivo para que la gente también se apunte. Entonces tendríamos que estar aquí a las 9:45. Se pueden dar diferentes tipos de charlas, no estamos restringidos a un tipo de charla en concreta, puede ser pues desde ponencias hasta charlas a personas de máster que se les quiere animar a hacer doctorado, cualquier tipo de charla estamos abiertos a ellas. Y luego se va a dar un certificado de asistencia. Esto es importante porque queremos también que luego se reconozca, como bien ha dicho Jimena, con horas de doctorado, vamos, de actividades formativas. Y bueno, lo que os he dicho, la idea luego es que demos un pequeño desayuno antes, 15 minutos antes de cada sesión. Y nada, simplemente deciros, pues eso, es que estamos un poco limitados ahora mismo de charlas, que por favor os apuntéis, que os apuntéis a dar una charla y que ahí tenéis los QRs para poderlos escanear y bueno, pues nada, os animamos a que os apuntéis, ¿vale? Y nada, ya, bueno, creo que como la charla, ¿no?
Sí, vamos, introducimos la...
Buenos días a todos. Voy a ser una persona que va a cambiar el idioma en inglés, ¿vale? So, the idea is for these talks also to be in English. So, if you want to have a conference that you can something like that, you can practice it here. I'm currently going to be only the person who is shortly going to introduce you our speakers. So, the first speaker for today is going to be Ana. I hope I'm pronouncing it right. Ana Carretero Perez. Ana is coming from the Electronic Systems Labs. She finished her bachelor's and master's also in communication here at UCM. But between 2018, while she finished her master's, she is working in the industry. And now she came back in 2022 to pursue her PhD and she's still working in science. So she's going to give us her talk in wearable devices for the diagnostics and treatment of neurologic diseases. Anna, the floor is yours.
Thank you very much for the presentation. Well, it's a pleasure for me to start with these meetings. This is the title of my presentation. So I am going to follow this index. I'm going to start with the motivation. Then I'm going to talk about the 2 wearables, the detection electroencephalogram and the transcranial magnetic stimulator. And we are going to end with the future of our work. Well, the motivation first is that I am an electronic engineer, so my presentation is focused in electronic components. So I try to be as divulgative as possible, but if you have any question, please don't hesitate to contact me. The general problem that we are going to address here is that with the increase of the neurologic disease, we have seen, like the stroke, the Parkinson, or the Alzheimer, we have seen that these treatments are limited because the diagnosis is usually delayed, and also when the diagnosis comes, the disease is advanced. So for the treatment, there are limitations because the patient has to go to the hospital to receive the treatment, and it spends time for the health staff and the system which they use for the treatments. So the idea to resolve this problem is the brain wearables, also for the diagnosis and the treatments. But what is a wearable? A wearable is an electronic device that can collect information from the body of the user and then process this information and show it to the user again with a file. But why do the wearables fix this problem? Because they are small, so that they can be portable. And these 2 points makes them working at any moment, in any place. This changes for the context because the doctor don't need to call the patients to the hospital. So no medical supervision is needed. But the main point of the wearables is that they are comfortable. But what changes will generate for neurologic disease and health paradigm? There are 5 points. The diagnosis, because as I said before, now the diagnosis will be sooner. For the treatments, because new treatments will arise. For the monitoring, because the doctor can know the information about their patient in any moment at any time, so that the time that this patient needs for the hospital is not needed now, so the medical attention will change. And also the cost, because the machines are very expensive at this moment. But for me, from the electronic point of view, it's a fight between the small size, the maximum autonomy, and the limited resources that a wearable can use. So we're working in a trade-off of these 3 points. Our hypothesis is to improve the diagnosis and the treatment of the neurologic disease using a closed-loop system. This closed-loop system is formed by 2 wearables. The EEG wearable, which recording and decoding the brain signals, and then the transcranial magnetic stimulator, which stimulates the neurons of our brain. So our objective is the acquisition, processing, and stimulation of brain signals in real time. So we have the EEG signal, then we process this information, and with this information we make decisions. With these decisions, we stimulate in the correct zone with the TBS. Well, these wearables can be used for lots of applications as Alzheimer or Parkinson, but I am going to focus in the stroke because it's the main objective of our project, which is Minación, and because in the rehabilitation of these post-stroke patients, when they think in a movement, then if we apply a magnetic field in that moment, we think, and the literature is with us, that they improve in terms of velocity, and the treatment is shorter. So the first wearable is the detection electrophonogram. This is a normal system that you can find in some hospitals, and it's formed by a machine and a cap of electrodes. Our approach is to use non-invasive electrodes and using a wearable with the small size, and the application file is the measuring movements detection, because as I said before, this can be very useful for the persons who has a stroke, and there are a lot of studies that can give us more information about this kind of signals. But how are we do this wearable? Well, we are going to study the number of electrodes, the input signal, the algorithms that we are going to use in terms of types and complexity, and also the trials, because we want the best performance. This is a normal signal that can be found when we record an electrode of a cap. You can see that there are lots of electrodes, but as I have said before, we are working with the imaginary signals so that the zones implicated are the ones that you can see in the slide. The primary motor cortex and the supplementary motor area as the mainly zones, and the other 3 zones that can be seen rounded by these 2 circles. But it's important to comment here that adding electrodes not always improves the performance. In fact, there is a threshold that we have demonstrated in the publication of the slide, so that this improvement is limited. The electrodes that we are going to use here are colored in the slide. We are going to use the 10-20 configuration, and you can see that there are electrodes in the 2 sides of the brain, because this makes us then to study the handedness. For the input signal, we have tested 3 databases because we want to study the acquisition frequency or sampling frequency. Because so we have a low, middle, and high frequency. In fact, the highest frequency is a database recorded by us using by this PCB, which also is developed by us. The movements that are recorded are open and closed left and right first, and the movement of the 5 fingers of the right hand. So in the case of the subjects, we have taken every subject as an independent element because we think that the brain plasticity makes the brain different. So we have to treat them as a different subjects. The sequence that we are going to follow is when we have the EEG signal, we filter in order to clear it. And for the algorithms, we have 2 types: the detections algorithms, with which are fast ICA core and FBCSSP, and for the classification we have the classification learner, which is a tool that gives us a lot of classificators. So the output of these algorithms are the decision if this input signal was a movement or not. For the test and results, I am going to divide this into general groups. The first one is the general movement versus no movement. Here first, I am going to select the database. So this image is shows the success rate for the 3 databases, the low, the middle, and the high. And as you can see, the best options are for low and for middle. In fact, low frequency is better than middle frequency, but as middle frequency gives us more data to work with, we are going to select the middle one. Well, for the algorithms, we have said in the first test that FBCSSP has low specificity, so we have discarded this algorithm. Then, for the other algorithm, which is fast ICA core, we have selected the complexity of 20 components because we have seen that if we increase these components, the success rate improves. In the image, you can see the success rates per 1, 2, 3, 4, and 9 electrodes for 3 subjects. And the results show that for ones with just 1 electrode, the success rate is the best one. So for specific movement, which is the other group of my tests and results, we have divided this in 2. First is the finger movement versus no movement. Here we have fixed the complexity and the trials as in the previous tests and results. And in the image we can see 1, 2, and 3 electrodes, 3 and 4 electrodes. Sorry. For in the case of 1 electrode, there is C3 and C4. Because, as I said before, we are going to study the handedness. And there are the 5 fingers, the thumb, index, middle, right, and pinky. And the success rate can see that is between 92 and 94%, which is a very good performance. For the last test and results, there is finger movement versus finger movement. Here we have included the movement as a movement in order to compare them with all the movements. You can see in the image the confusion matrices of C3 and C4 and the success rate of all of them. Now, adding electrodes, we want to see if improves the success rate or not. This is for 2 electrodes where we can see that it's worse. Same happens to 3 electrodes and same happens with 4 electrodes. So the conclusions is that we have a sampling frequency for our wearable, we have an algorithm, the complexity and the trial selected, and the electrodes, they are going to be C3 or C4 dependent of the handedness of the user. So the technology challenge for the wearable EEG is to develop a wearable that can do this processing items in real time, and it has to be small, modular, configurable, portable, and autonomous. So for the transcranial magnetic stimulation, which is the second wearable, first I am going to talk about this kind of stimulation. This stimulation is an electric field that is generated in the brain when a magnetic field is generated by the coil, which is this element in black. This is a normal system that can be found in the hospitals where there is a machine and a big coil, which is this. Well, our approach here is use the imagery signals that we have detected before, and then apply the magnetic field for the post-stroke patients. This kind of stimulation has 2 protocols, which are CTBS and ETBS, which follows the sequence of the slide. In the literature, there are studies that using theta band, but we are going to work with more frequencies between 1 Hz and 1 kHz. How we are going to do that? We are going to develop an array of coils so that we can test the number of coils and also the type of coils that we are going to use, because the current that can pass through them is different, so that the shape that the waveform is different. With this, we expect to excite the brain, but not only excite, but have complete control of the sound and the dip. The 2 stimulators that we are going to use are the TMS board stimulation. We have 2 coils, these ones, where the maximum magnetic field is rounded by in red here in the middle. This PCB led us to test the magnetic field using a continuous signal of severance. For the do-it-yourself stimulator, this one led us to working with different frequencies between 1 Hz and 1 kHz. These are the tests and results. At this point, we have used mice for our proofs. So for the TMS board, we expect to see the magnetic field that can be seen below the head of a mouse. For doing this, we have used a dosimeter. These are the results. The different tests are with and without mouse, in order to see this absorption of the signal by the brain. The results show that the 50% is absorbed by the brain in any case. So for the do-it-yourself board, we expect to see the electric field that we can see when we stimulate with different frequencies. So we have put an electrode in the brain of the mouse, and then we stimulate with different frequencies. We can see here the electric field generated in the brain with a 5 Hz signal, and this is for a 10 Hz signal at right. You can see the differences between these 2 signals. So the conclusions is that the permittivity obtained is in range, and in the case of the excitation with different frequencies, we can say that we stimulate the brain with the frequency that we want. So the technology challenge here is similar to the wearable EEG. In fact, there are a lot of features that are common, like small, modular, portable, and autonomous. But in this case, we want that this wearable has configurable coils so that we can control the magnetic field in all the aspects that we want. So for the future, we want a post-stroke system that lead us to be helpful for the patients in their treatment and in their recovery. This system will have two wearables: the wearable EEG, so that we can know when a patient wants to move, and then the other wearable will stimulate when when we detect that they want to move. Because this is good for this kind of patients. So this system is pretended to be tested in vitro and in vivo. I focused on the stroke, but as I said before, this can be used for so many applications as the Alzheimer, the Parkinson, or even the depression. So this is the end of my presentation. Thank you very much for hearing me. I hope you enjoy. Please tell me if you have any doubt. Thank you very much again.
Do you have any questions?
Thank you for the talk, first of all. I was wondering, because I don't know if I didn't understand correctly, but the idea is that it detects when you want to do a certain movement, and then it doesn't induce the movement, but rather it finishes the connection within the brain of what that movement would entail, or what is like the whole process of.
Okay, the process starts when you think in a movement, so that when you move, it's easy because you move. But when people cannot move, they think in the movement. So we can detect when this movement is stopped in their brains. In that moment, we pretend to apply this magnetic field because the literature said that for this kind of patients, this improves a lot their recovery.
Thank you. The question is also related to the one from Pablo. I mean, if the patient would like to do several movements, like one is the hand, another is the moving the leg, then you need to apply this field in different zones in the brain, or you're always applying the field in the same region of the brain?
In the same region, because the imaginary movement zone of all brains are in the same place. The difference is that if you are handedness, because your tendency is to use the left part of your body, the right part of your body. So you can select the electrode in the left part or in the right part. But for all movements, it's in the same part of the brain.
Okay, three short questions. First of all, congratulations for your talk and congratulations for your work, because I think it's very interesting. When you talk about the filter of the encephalogram signal, which type of filter do you apply to the signal? What are you searching to extract from the signal?
It's a bandpass filter because I'm interested in the signal between 0.5 Hz to 150 Hz, because all the literature says that the EEG signals are in this range. So this is the range that I have used to filter.
Okay, but you don't need to filter like noise in the signal?
Oh yeah, our noise because the signal have noise in the more higher frequencies, and also I don't say that, but the electric noise, which is 50 Hertz here and 60 Hertz in United States, is filtered too with a notch filter.
And after that, you say you use like classification learning.
Yes.
And how this classification works? It's with deep learning algorithms, or you do a classification based on the specific type of matching signals or something.
Well, from the detection algorithms, I have lot of characteristics of my signal. So these characteristics pass to the classification learner, and I don't implement any classification as a tool, so that you select the input using the classifications they have, and then you have an output.
It's like a black box.
Yes, for me now it's a black box, because I now only study the detection algorithms, which are the ones that I have implemented.
And the last question is because I was a little bit shocked. You say you can apply your research on Alzheimer, stroke, and depression. And my curiosity is about how do you apply this on depression? Because what I thought it's that depression, or currently the treatments of depression leads more with hormones, with some specific, let's say, chemical processes of the brain, but I'm not, I don't know at all any of this.
Well, we think that it's a fact that when you stimulate the brain, your neurons make connections. So in some way, you have changed. When you apply a magnetic field, you have changed your mind, because you have created these connections. So these connections can help to the depression processes. For example, I don't know in which way this can be used, but now there are some studies that are using the stimulation to excite the brain, so that it improves in some way. I don't know how to say more, but they are using this.
Thank you very much.
Thank you, that's all for this talk. Thank you very much for the talk, and let's give So, I have a second speaker for today. The second speaker for today is Isabel Lopez de Vigo. I read it right. She's coming from Biomagnetism Lab. She also pursued her first steps of her career, so her bachelor's and master's in UPM in biomedical engineering, and she did her master's in Centro de Tecnología Biomédica. I hope that translates as. She is currently in the Biomedical Lab as a PhD student on the project funded by the Humanism and Science Foundation in collaboration with UPM. The project is started in 2022. So she's going to give her talk in Can Electromagnetic Fields Modulate Cellular Activity? And without hoping, I hope that I'm not giving any spoilers out, but I would like to read you the question from the abstract that I think is the main question. Is could we achieve opposite effects on cell behavior using the same magnetic field depending on the nature of the cell line? Talking about tumor and non-tumors. So Isabel, thank you.
So good morning, guys. Thank you very much for coming today to this talk entitled Magnetic Field Modulate Cellular Activity thank you very much to great talk organizer, because I think that it's a great activity. So, well, let's start with a brief introduction about me and the laboratory in which I work. Well, I studied the degree and the master degree in biomedical engineering here at the ETSIT. And now I'm in my third year of the PhD program in biomedical engineering. And well, when I was studying the degree, I quickly realized that I love research and science. So I love medicine and biology. And the solution that we as biomedical engineering could provide as medical doctor and the patient. So I always ask myself the same question, that is, can an engineer go into basic research, because I love cells? And I can already tell you that the answer is yes. So this is my team. Well, I work in the bioelectromagnetic laboratory. It is in Biomedical Technology Center at the Ciclo campus. For those of you that do not know what is the center, it is a multidisciplinary center that houses different laboratories that work in biology and medicine, applying engineering and biotechnology. So, well, our principal investigator is Dr. who is a full professor in the biomedical engineering degree, and who is the supervisor of my thesis. And well, if I have to highlight the strongest points of our laboratory is its multidisciplinarity, because you can find electronic engineers, biomedical engineers, and medical doctors working together to respond some question of science from an engineering and biological point of view. So, well, what are our research lines? In the first place, we study biological effects of electromagnetic field. So we perform some in vitro studies of the effects of electromagnetic field in tumor and non-tumor cells. I talk later in more detail about this line of research, because it's the line of my thesis. In the second place, we measure electromagnetic field in the radio frequency band. So we have the main objective of ensuring compliance with regulation in the mobile phone band, mainly in the radio frequency band. And well, we design a personal exposimeter to record personal exposure measurement in the radio frequency band. That is the final project of my colleague, Marco Rivero. And well, in the last place, we developed device for the therapeutic application of electromagnetic fields. We have a transcranial magnetic stimulation device that is this helmet. It is composed by some coils, and it generates a weak electromagnetic field. So we can modulate the signal of typical diseases such as fibromyalgia, depression, or migraines. It is actually in use in some private clinics such as Quirón or Ruber, and el Hospital del Tajo here in Spain. And well, we designed too a globe that is for the treatment of arthritis and arthrosis. And it's the same, it generates a magnetic field in the joints to make the fiber grow in the direction of the magnetic field. So we could put it in the patient. And well, it's for the treatment too. So, well, let's start with an introduction about electromagnetic fields and bioelectromagnetics. And well, what is an electromagnetic field? It is a combination of electromagnetic waves that move simultaneously because of the movement or oscillation of electric surfaces. So here in the electromagnetic spectrum, we found the different electromagnetic waves. And well, we can divide it in ionizing and non-ionizing side. So the ionizing radiation is able to break the molecular structure of the biological tissue, whereas the non-ionizing radiation has not this capacity, because it has a lower energy. So it will soon, this part of the electromagnetic spectrum, we found from 0 Hz up to 300 Hz the very low frequency electromagnetic field that are the electromagnetic fields I use in my thesis. And well, for example, we found it in the frequency of the electricity grid in Spain, that is in 50 Hertz. So, well, what parameters are important in the electromagnetic fields? Well, we found intensity, that is the signal amplitude, the wavelength, that is the physical distance between 2 points from which the wave repeats, and the frequency that measures the number of cycles of repetition of the wave per unit of time, and is the inverse of the wavelength. So if we have a low frequency electromagnetic field, we have a larger wavelength, but we have few repetitions per unit of time. And if we have a high frequency electromagnetic field, we use a shorter wavelength, but we have more repetition. So I use the low frequency electromagnetic field in my test. Well, what is bioelectromagnetism? It's the study of the interaction between the electromagnetic fields and biological systems. And typically, these experiments are like this. We use a cell culture plate, that is the exposure plate, and we exposure it to an electromagnetic field with a specific intensity, frequency, and waveform for a period of time. And we compare the result we obtain in this culture plate with the other, that is the non-exposed or controlled cell culture plate, in the same period of time. So we measure some cellular processes that are typically studied. For example, the variability, that is the percentage of cells that are alive in a population of cells. And we answer the question, does exposure make cells live longer or shorter? The proliferation, that is the rate of division of a cell in a population. So that exposure makes cells divide more or less. The apoptosis, that is the process in which the cell decides to die because it's something wrong. So that exposure causes cells to die more. The oxidative stress, that is the process in which the cell can produce some toxic products, and that exposure causes cells to undergo stress. So let's move to our experiments, our experimental model, our main objectives, experimental methodology, and our expectation of future lines. So, well, we use 2 cell lines. In the first place, we use mouse astrocytes. Astrocytes are glial cells that are supportive cells for neurons that participate in their current function and perform important function too. So then we use the mouse glioblastoma, that is the tumor cell line of the astrocyte, and it is a fast-growing, very aggressive astrocyte tumor. So the incidence is between 3 to 4 cases per 100,000 people, and it has a very poor prognosis. Well, our main hypothesis is that there are specific electromagnetic field parameters for which cells modify their process. So we use, as I said, the glioblastoma and astrocyte cells, but we compare to the glioblastoma with other tumor lines, like breast cancer, neuroblastoma, or pheochromocytoma. And we would like to answer the question, do tumor and non-tumor cells respond differently to the same magnetic field? And well, we use different parameters. So when we perform the experiments, we always vary one parameter and fix the other. So if we choose the frequency, we vary frequency, but we fix the exposure time, the intensity, and the waveform. So we can answer the question, do cells respond differently to changes in different parameters? And finally, we have to study cellular process when we choose the cell type and the parameters. So we study viability, proliferation, oxidative stress, and apoptosis. And we answer the question, can we modulate a particular cellular process through a magnetic field? Well, our experimental methodology consists of a pair of coils that are like this. So we connect them to a field generator, and we create a magnetic field in the center of the coil. So we put the cell in the center. Actually, it is not the system that we use because we have designed our own exposure system, but it is currently under review and patent process, so I cannot show you today. And well, my thesis goal is to obtain a combination of electromagnetic field parameters with which to achieve tumor cell reduction while keeping healthy cells undisturbed. But we have a very big objective in the future, that is deciphering the cellular mechanism by which cells respond to particular combination of electromagnetic field parameters. So to sum up a few conclusions, what do we do? That is the application of electromagnetic field to tumor and non-tumor cells by changing parameters of frequency, intensity, and time. How? Well, we use coils to create a magnetic field and apply this magnetic field to culture of glioblastoma cell and astrocytes. And why? Because we have the hypothesis that each cell is sensitive to a certain magnetic field with a certain frequency, intensity, and waveform. So we would like to modulate cellular response. And I would not like to finish my presentation without encouraging you to come and bring your own ideas. We are a lab open to science. We lower for to hearing from you. So thank you very much for your attention. And this is all.
Congratulations for your comment. You used a word that I didn't. I'm very ignorant about this. What is prognosis?
The prognosis is that well, when you have a disease and the medical doctor well expect that you live some years, so is the prognosis, the time you can alive when you are at the diagnosis.
And one curiosity about the magnetic field you are applying. It's a continuous magnetic field, or it's, I mean, does the direction of the magnetic field change, or it's only you put your samples into that coils and the magnetic field is always the same?
Okay, well, now we use a square waveform, and we change the frequency, but it is a continuous wave, a continuous exposition. So we put the cell and we use 72 hours. So we take the sample in 24, 48, and 72. So, but the exposure is continuous. But we want to change it and to make an intermittent exposure or what's the difference in the results. But it's a continuous way.
Thank you.
There was a question there.
First of all, thanks for the presentation. And I have a similar question as the previous one. Was about the time that you exposure the cells, because I don't know if they have to die to finish the experiment, like they are going to see when they die or.
Yes, well, we now using 24, 48, and 72 hours, but we culture cells 24 before we expose cells. So we use 5 days. We put the cells, we turn on the exposure, and we obtain the result of the cells. The cells are alive at 72 hours. But we look for the difference in the behavior in control and exposed cells. So we use this time because are usually used in this type of experiments, but we want to reduce the time too. So that is in the future experiments.
Maybe add to the parameters like frequency and waveform and polarity. Like horizontal or vertical or circular polarity?
Well, we use only now when we use this type of coils, sorry, well, the electromagnetic field is in this direction, so we only use this at the moment. I don't know if we change it in the future, but for now not.
Okay, thank you very much for your presentation. I have a question. After the exposure of on the cells, what are the techniques you use to like analyze how the cell?
Okay,
is
we
doing after
use
that?
for viability the entity test, and that is to measure the metabolic activity of the cells. So we use absorbance techniques. And then for the proliferation, we use trip and blue and an automatic counter of cell. And the trip and blue enter in the cell when it's done.
Okay.
And well, from apoptosis, we use annexine 5. That is a protein that binds the membrane when the cell dies. And we use fluorescent techniques. And oxidative stress is the same with fluorescence.
Okay, thank you.
Thank you very much for the talk. You said before you were using two different types of cells from different
Yes.
parts of mice. Do you test on the cells or on tissue in a way? And does the behavior change in between using individual cells or cells within a tissue?
I have the hypothesis that it changes in the cell from the tissue and from the organ of the system. But well, we have to start with in vitro studies. So I would like to test all the results of my thesis then in vivo models, because I think that's all changed. But well, we have to start with something, and we choose the cell model, because the main objective of my thesis is to understand how parameters can change the cell behavior. So it is more like that we would like to find how the parameter acts in the cell.
Thank you for your anything else. Do you measure free parameter while you are applying your family field to the group, like temperature of the, just in case there is some change because you do some resonance
Yes.
happening inside the.
I would like to do it, but it's very difficult because we have to expose cells, and we need some like microscope that puts inside the incubator. So it's very difficult because we have to use some proofs, some fluorescent proofs or something like that to measure the change, and while we are stimulating. So and cells can live without the incubator 1 hour or something like this. So we are not able to do it, but it's interesting to look for it.
Thanks.
Which is the intensity of the magnetic field? Well, first of all, thank you for the presentation. Which is the intensity of the magnetic field?
Well, we use 100 microtesla now, because when we maintain the intensity, because it's the legal limit in Spain for frequency of 50 Hertz, but we would like to use lower and higher intensity when we look for the difference in intensity. I think that up to 1 millitesla, no more.
Okay, so thank you so much.